Samuels here with a continuation of our discussion of equilibrium. Last we left off, we were discussing Le Chatelier's principle, which tells us that when you have a system at equilibrium and you try to disturb that equilibrium, the system will shift to minimize that change. So for example, if we add reactants, since those are things on the left side of a chemical equation, the equilibrium will shift to the right to try to get rid of those reactants. If we add products, since those are on the right, the system will shift to left to get rid of those. If you add heat, it shifts to the side with less energy, and if you add pressure, it shifts to the side with less molecules. You can find those by counting the coefficients and adding them up. So let's do some practice with that. Why don't you pause the video now and try to go over these 4 problems. Write down what do you think would happen to the equilibrium if we did these things. Okay, so now that you've gone over those, let's go over the answers. If we add heat, the system would shift left towards the reactants. Since heat's a form of energy, we've got more energy on the right. By breaking water up into hydrogen and oxygen, it would bring that temperature back down. It would absorb some of that heat, and so the system would shift left. Adding pressure would shift this system to the right. If we count up the molecules on the reactant side, we've got 2 hydrogens and 1 oxygen. That makes 3 compared to 2 here. Do not count energy, as that is not a molecule, it's not a substance. It's just energy, or heat. So 3 on the left, 2 on the right. Adding pressure would shift the equilibrium toward the products to the right. If we add products, those are on the right, it would shift left. If we add reactants, it would shift right. All right, if you ever see remove or decrease, just go the opposite way, because the system will try to get those things back. Now, let's look at some of the mathematics involved in equilibrium. The equilibrium constant K gives us an idea. Here's a generic chemical equation, lowercase letters being coefficients, uppercase being chemical formulas for different substances. The equilibrium constant K is defined as the concentration, that's what those brackets mean, okay, of the products here, divided by the concentration of the reactants, okay, we multiply those, but we bring them to the power of the coefficients. And if we basically look at this, what you'll find is that the larger the K value, the more products we have, and the lower the K value, the more reactants we have. It kind of tells you where the balance lies in the system. Now be careful, A, B, C, and D, they're generic. There might just be one reactant. In some cases there may be 4 products, who knows. These are just generic for however many terms you have on each side. So this altogether, K equals, all of this is called the equilibrium expression. And as I said, if you have larger values, it means the products are favored. And if you have lower K values, it means there's a lot more reactants. So let's look at an example. Write the equilibrium expression for this chemical reaction, water and carbon monoxide, forming hydrogen carbon dioxide. So remember, in that general form, K is the products divided by the reactants. So instead of plus, we have no plus here now. These are multiplied. These concentrations divided by the concentrations of the reactants, and since all the invisible coefficients were 1, all the exponents were 1. If there's a 2 here, for example, you would just put squared instead of 1. Or if there was a 3 here, you'd put a 3 here, be to the 3rd power. So let's look now at one in, actually let's give you guys a chance to practice first. Go ahead and write the equilibrium expressions for each of these. You can pause now. Okay, so now that you've tried those, hopefully you saw you had 2 things on the top, 1 on the bottom, no plus signs, no exponents. Hopefully you squared the concentration to H2, squared the H2O on the top there. So in this case, we only have A, B, and C. There is no D. And hopefully on that last one, again, no plus signs, and each of these coefficients became exponents. Now let's look at one involving actual measurements. An 8-liter vessel at 15 degrees Celsius contains a 1.5 molar N2O4 at equilibrium with 0.7 molar NO2. Here's the equation here that shows the relationship between those 2 substances. So in order to do this, we start like before by writing the equilibrium expression. If we're asked to calculate the equilibrium constant, we'll need to plug it in. We've got products, concentration of the products on top, coefficients become exponents, and then we just plug in the numbers. If you look here, here's your concentration of NO2, so we plugged that in there, squared it, and divided by 1.5 to get 0.327. This is the equilibrium constant for these conditions. Notice, like pH, there are no units here. This is another safe place for naked numbers. We don't need units there because you'd get weird things with the squareds and the molarities and everything. But the stuff you're plugging in here is technically molar. We just leave units out when it comes to the answer because this is just a constant, not a measurement. Okay, so let's look at another practice problem. You can do this on your own. Pause the video, try it out. Okay, and what you should have come up with is either this number here or this. Remember, these mean the same thing. 10 to the minus 3 just means boom, boom, boom. Okay, so we got 3 significant figures either there. Make sure you're rounding properly in this case. All right, so let's make sure we understand what these mean. All right, if you see this low equilibrium constant, think for a second, what does that tell us? Well, what that tells us is we have all 3 of these chemicals in the same container, and that occasionally nitrogen and hydrogen are forming ammonia. It's saying that actually, since we have a low K value, definitely less than 1, it means we have a lot more reactants than products. That under these conditions, this temperature, etc., then we don't have a very big presence of NH3. It's mostly this stuff, not much here. If you had a large number, like 10, it would mean the opposite. We have much more product. All right, that's all for now. Hope you enjoyed.